Okay. So this is active learning. So you guys are going to have, working at the same time I do. Okay. So the first question says, what is the base current on the 161 kV side of the transformer? So how would we figure out that? Let's see. And here, if you're looking for positive numbers, you should be fine with this.
Oh yeah, I got it figured out.
Oh, you got it figured out. You had like the absolute value.
Those in the green are not real.
Oh.
Yeah.
Oh, okay. So for A, we're going to have I base 161 kV. And that's going to equal what? S base over square root of 3 times the kV base. Oh, sorry. Uh-oh. Oh, there you go, eh? Okay. Because, S3 phase equals square root of 3 VI, right? Where this is the line-to-line voltage. Okay. So that's how we're getting that. So what is our S base? Clay, do you? Oh, you can't really see it that well, can you? Okay. S base is 50 MVA. Square root of 3 times 161 kV. Okay. Ooh. Okay. So there we go. There we go. Okay, so 50, oh, not 55, clear. I0, and that's mega, right? So that's PE. Oh, man. Where's the EE button on here? Oh, right there. Second EE, 6, divided by parentheses, square root of 3. Times 161, yep, 161, and that's to the third. So everyone gets the same answer right there, 179.3. Units there would be amps. Okay. Second question, what is the base current on the 34.5 kV side? Yeah, you just have to use a different kV, right? Yeah. So I base 34.5 kV is going to equal 50 MVA divided by the square root of 3 times 34.5 kV. Oh, one thing to note, Dan Gervais sent me an email, and it sounds like they're going to be able to do tours this semester. So yeah. So guess it doesn't let me go back up. Okay, so we'll just do 50 to the 6. Oh, back up 1 divided by parentheses second square root of 3. Oh man. Delete 3. There we go. Over this way a little bit. Delete times 34.5. 3. And there we go with that answer. Oh, 836.7 amps. Everyone get the same answer? 836.7? Okay. Next one, that would be C. We want Z base. And remember, one of the ways of doing this is just taking the KV squared over the MVA. Okay, 10 to the third squared is 10 to the 6, right? And MVA is 10 to the 6. So those two cancel out. And so all I have to do is put in the number here, 161 squared divided by 50. And that'll give you your Z base. And again, the volts would cancel. And so one of the volts, I should say, would cancel. So you're left with volts over amps. So that's ohms. So that's a good thing, right? So what kind of answer did people get for that one? $518.4 ohms. Everyone agree with that? Okay. Clay, can you see it okay?
Yep.
Anybody hear what he said? Oh, okay.
Yeah, I can.
No, it's up all the way. Okay. Maybe Clay's got a chat window or something like that. I don't know. Okay. So hopefully Clay is getting it. Okay. So D, Z base. Now this was Z base for the 161, right? This is Z base for the 34.5. Again, it's going to be the same formula. $34.5. We leave out the K. We're going to square that divided by 50. Right? What do you get there? 23.805 maybe?
Yeah.
23.805 ohms. Okay. Okay, for the next one, what are we asking for part E? What is the impedance in ohms looking from the 161 kV side of the transformer? Well, we know that the transformer is 10% impedance, and we just calculated Z base, right? Okay. So here's E, and we're looking for, well, Z per unit is equal to Z actual over Z base. That's the standard formula, but now we're looking for Z actual. So that means that Z actual will equal yeah, Z base times ZPU. Okay, so Z base, we said 161 kV side is 518.4. So we get 518.4. And what is 10% in per unit? 0.10. There you go. So I think that's going to be like 51.84 ohms. That's about right, eh? Yep. Everyone see that? We're taking Z actual equals Z base, 518.4 times the per unit value. 10% is 0.1 in per unit, right? Any questions on that? So that was E. What are the per unit values for 100 MVA base? So we need to change our base. Okay. So F, we've got Z2 per unit equals Z1 per unit times the ratio MVA. This is 2, and this is going to be 1, times KV1, and that's going to be squared, divided by KV2, and that'll also be squared, okay? Now, in this problem, we're not changing the voltage. All we're changing is the system base, right? So, stays the same. Okay, so that's 1 over, excuse me, that's, what? So the KV1 and KV2, we're not changing the KV, right? Because it says, what are the per unit values for 100 MVA base? Okay. So we're not changing the voltages at all, right? So Z 100 MVA is going to equal, well, the transformer was 10%, so that's 0.01. And then the new base is 100 MVA. And the old base was 50 MVA, right? Is that making sense? So what is the new value going to be?
I got 20 milli.
200 milli, okay. And another way to represent that would be 0.02, right? Per unit. There's no ohms or anything like that on there, okay? So if the system map that we have is 100 MVA base, and we're just adding this one transformer to it, it wouldn't make sense to change everything else in the system to 50 MVA. We just need to change that one transformer to 100 MVA, okay? And the 161 kV for the 161 kV system, well, that should be the same. And the 34.5 for the 34.5 kV system should be the same. So we're not changing the voltages, okay? Sometimes you'll change the voltages for generators, Because let's say the generator rated is 25 and you're only outputting 22.5. Okay, so you'll have to adjust the percent impedance of the generator for both voltage and MVA. Does that make sense? Okay, so sometimes you do use the kVA too. Is that making sense? So this 1 times kVA 1 squared over MVA, well, that's the formula that we had for side 1, and then this is MVA base 2 over kVA squared. That's the formula that we would have for the base 2. Okay, so that's where that formula comes from. Is that making sense? Okay.
Could you put 20 to the side too? Or do you want to be added?
Oh, but you'd have to do it like this. Right? Any questions on any of those? Okay, next we're going to look at an entire system. Okay, so here's an entire system. So we've got a big generator over here, and then let's say we have a sawmill over here that has a lot of motor loads. Okay. We've got 2 transmission lines going between the generator and the motor or the load. Okay. One's at 220 kV, the other one's 110 kV. We notice the transformers though, T1 is 22 to 220, T2 is 220 to 11, T3 down here is 22 to 110, and T4 over here is 110 to 11. Okay, so it looks like over here we can keep that base, right? Because that's what we're using here and here. Does everyone see that? So on this side of the transformer, everything is rated at 22 kV. Okay. How about over on this side? This guy's rated at 10.45. Both of these transformers are 11K over here. So here we're going to have to use the voltage in addition to the MVA base. Okay. Is that making sense? Cool. Okay. So that network can be represented by these impedances on here. Okay. So let's calculate what all these are going to be. Is everyone on the same page as me? Hopefully. Okay, we'll start over on the generator side. That's the simpler side. The first thing we have to do is pick a base. The most common base is 100 MVA. So pick 100 MVA as your system base. And that's a typical value. Okay. Now, as it turns out in this drawing, nothing is rated at 100 MVA. We got the generator is rated at 90 MVA. This guy here, 66.5 MVA, but nothing. Oh, and the transformers, 50, 40, 40, 40. Okay. So if you were just doing this problem, it might make sense to switch everything to a 40 MVA base. But again, if you want to be more generic, just make everything 100. Okay. So the first thing we have to do is come up with the new per unit values. So X on the generator. What was the old value? .18. So that's how we started. And where's our formula here? Right here. MVA over MVA, KV over KV. So we're going to 100 MVA, right? So 100 MVA, that's our new base. And the generator itself is a 90 MVA, right? Okay. And then the voltage, 22 kV over 22 kV. You square both of those. What's 1 squared? 1 is still 1. Okay? Does that make sense to everybody? Okay. I keep pushing that paper up. I'm sorry. So what's the new value going to be?
.2.
0.2. And again, if you want to represent that in percent, that would be 20%. Okay? And this 0.18, we get right off the nameplate of the generator. Okay? The nameplate of the generators would say it's a 90 MVA generator at 22 kV with an impedance of 0.18. Okay? And then all you have to do is change base to put it into your system model. Okay. XT1. So this is the first transformer. What's its impedance? Point 1. What is that transformer rated at? We know the new system base is going to be 100 MVA, but what is that? Transformer said it's a 1% impedance, excuse me, 10% impedance, or 0.1 per unit. But what's the MVA rating of that transformer? 50 MVA? And again, we're going to do 22 squared over 22 squared. Okay. So that's still going to be 1. So what do you get there? 0.2, right? And then we got XT2. What's on the nameplate of XT2? What?
0.06.
0.06. So how much is that? Oh, that's so it's a 6%. And 0.06. Oh, I almost messed that one up big time. Okay, what's the and 100 on the top? 40 on the bottom, you said? Okay. And 1 squared, we don't have to worry about that because the voltage is the same, right? 22 kV and 22 kV.
220 to 11.
Oh, okay, but we're not changing the 220
Oh,
or the 11. We don't have a different voltage. right? So yeah, I agree with you. This transformer T2 is 220 to 11, but we've got 220 volts here, and we've got 11 kV there, so we're not changing the voltage on either side. We can get into tap changing transformers and stuff like that. That would be a lot of fun, but we only have so much time in this class, so usually the transformers will be the voltage, that's the rated voltage, right? Okay, so what's that going to equal? 0.15 per unit, XT3. What's that guy equal to? 0.064 times 100 MVA over 40 MVA, right? So what do we get there? Point 0.16. Okay, that's looking good. Oh, we've got one more transformer to go. X transformer 4. 0.08. Again, 100 MV base is where we're going to. The nameplate is based on the rating of the transformer, which is 40 MVA. So what do we get for that guy? Point two. Oh, sorry. Yawning. Okay. Now we have ohmic values for the transmission lines. So we got to come up with a base, Z base, for the 220 kV. What's that going to be equal to? Nobody come up with the base before? Yep. Okay. So the kV squared would be 220 kV. But again, if you use kV and MVA, you don't have to include the units. So that's going to be 220 squared over, what's our MVA base? Yeah, yeah. Remember, 100 is our base. So everything has to be on the same base, otherwise you can't add them up. Okay. So what do we get for that? $484, and those that would be ohms, right? So if we want to get Z line number 1, well, what's the actual value? Oh, no, impedance value. What's the actual impedance value of that line? 48.4. There you go. 48.4 ohms. It's on the table. Divided by, oh, that's nice, 484 ohms. So what's that going to equal? Point 0.1. And again, that's a per unit value. Z base 110 kV, 110 squared over 100 MVA. What do we get there? 121 ohms. Everyone get the same thing? So Z line number 2 is going to equal what? What's the ohmic value for that transmission line? What?
65.43.
55 point,
65.
oh, 65. Good thing I'm writing in pencil here. 65.42.
43.
I gotta put my, oh, 65.43. That's what you were saying. Okay, 65.43. 6543. Oh, that's nice, right? It's a nice number. Okay, so, and then our base was 121 ohms and ohms. So this thing's not gonna have any units. So what do we get there?
540.7.
540.7. Oh, yeah, let's go there. 0.54. You were giving me a percent, eh? Okay, 0.7 per unit. Okay. I like putting per unit there just to remind me that, yeah, this is per unit. Okay, and it also prevent me from putting ohms there, right? Because there's no such thing as ohms per unit. Okay. Questions on that? So we need to now, we got all the impedances here for this guy. What we're left with are these two guys over here. Okay? Does that make sense? So we got to come up with a number for the motor. So X for the motor. Well, we can do it the same way we've been doing it for the transformers. Is there a per unit or percent number on the motor? 0.185. Okay. We want to switch it up to 100 MVA base. So what's the base on the nameplate for the motor? 66.5 MVA. Okay, but here's where we're going to actually use the voltage. Okay, so it's the voltage that we came from versus the voltage that we're going to. So what's the rated voltage on that motor? 10.45 kV squared. And what's the line voltage? 11. 11 kV. Okay, so the kVs cancel, the MVAs cancel, but you have 10.45 squared over 11 squared here, right? So you've got X motor, a little bit lower down, X motor equals 0.185 times 100. I'm just leaving off the MVAs because they're going to cancel out over 66.5 times 10.45 squared over 11 squared. So I just took out the units to make it look prettier. 251.1. Okay, there we go. And that's per unit. All right, the next number after, so this was 1.
It's like 0.25107.
Oh yeah, 07. Okay, so that would make this the fourth digit 1.
Yeah.
Yeah. Okay, good. Okay, let's see here. We've got one more thing to do. No, we did the generator already. That was the first thing we did, I think. So the generator we got, next, the transformer 1, transformer 3, transformer 4, transformer 2, X1, the transmission line 1, transmission line 2, we've got, and we got the motor. We got this load right here that we have to try to figure out. So how are we going to come up with an impedance for that load? So it's this guy right here. So all these other things we can model as inductors. Can we model this guy as just an inductor? No, right? Okay. So that's a resistor and an inductor in series, right? So, let's see, where's my sheet? Oh, here we go. There we go. Okay. That's good. So how big is the load?
10.45 kV.
No, I want to do like a power triangle thing. Yeah, the voltage is 10.45 kV, right? Okay, but this guy here is 57 MVA. And we got a power factor of what?
0.6.
0.6. Okay, lagging. So that means 0.6 equals P over 57 MVA. All right? Because that's the definition of power factor. Power factor equals P over S. Okay. So solving for P, we have P equals what? 0.6 times 57 MVA. What does that equal? Three 34.2 MW, right? Because real power is that. So 34.2 MW. And what's Q going to equal? Well, one way we can get it is to take 57 squared and subtract 34.2. Now, are you guys comfortable with that 34.2 that you came up with me? I'll do it on my calculator just to make sure. 0.6 times 57, 34.2 exactly. Looks good. So what's our Q? 45.6. And that's MVAR. Okay. Okay, now how can we represent this guy? These two are in series. So I've got a resistor that's 34.2 megawatts. And then I've got an inductor that's 45.6 MVAR. 45.6. Now, in the per unit world, S is just equal to V times I, right? Does everyone agree with that? Okay, and we know that Z equals V over I. So is there a way for us to go from megawatts to V times I and figure out what I is going to be? So we know V,
The voltage of the load,
yeah, the voltage of the load is what?
10.45.
Yeah, 10.45, right? So what? Okay, we're almost out of time. So all we have to do is figure out that impedance. And we have this total system impedance, okay? And we can calculate faults on each part of the grid. So that's per unit and percent. Okay. Now, oh, yep, they can hear us. Let's go back here. So on February 8th, I've got another assignment for you. It's visible now. And it's very similar to the problem that we just did. Okay. So I've got questions 1, 2, 3. Oh, okay. I want to go back here. Y connected generator. There we go. Ah, I still can't see. There you go. Here's the nameplate of the generator, the reactance, and per unit. You have to figure that out at ohms. Now, did we do that today? Yeah. All right.
Does it give you a new base to use?
What?
Does it tell you what new base to use?
The nameplate says it's 200 MVA. So you always use, this is all the stuff on the nameplate. So whatever the nameplate MVA is and the nameplate KV, That's how you can figure out the actual ohms. Okay? So if they give it to you in percent, you gotta convert it over to per unit. And, well, that's an awful big per unit impedance, but I guess so. Okay, and then, question number 2. We're gonna take that per unit value that we came up with in, question 1, and we're gonna change the base to 200, excuse me, from 200 to 100, and from 20 kV to 13.8 kV. Okay, so that's that formula that we have. That's the ratio of the MVs over the ratio of the times the ratio of the KVs. Using the new base values, convert the per unit answer calculated in question 2 to ohms. Okay, so those are those first 3, and then the second 3 have to do with this picture here. Okay. And we're switching bases. So it's all the stuff we did today. Okay? There's no load on here, so it's okay that we didn't do the load. Okay? So you right now have enough information to do this thing. Okay? Okay. And when was it due again? February 8th. So you got a week to do it, right? But I want to put off, yeah, closes at midnight next week. Okay? Sounds good.